Hello everyone. So today we will be presenting Vani, which is a programming language we developed as a part of SER 502 course under Dr. Ajay Bansal. So let me introduce you to our team members. Myself, Prerana Kumsi.
I'm Aditya Kumar.
And I'm Samuel Lana.
And I'm Aditya Murarka.
So Vani is a Gen Z inspired programming language, which we have designed to make coding more fun and expressive while still being rooted in logic and structure. So we built it using Prolog as the base because Prolog helps us in implementing things like parsing and evaluation in a very declarative and modular way. Our target audience is beginner programmers, students, or really anyone who's curious about coding and wants to try something more creative, expressive, and less formal. So the gap we noticed is that most programming languages today focus so much on structure and efficiency that they lose the element of fun. So we decided to flip that and build something more playful on purpose. Coming to the grammar. So the grammar for Vani is written using DCGs in Prolog, which behave similarly to BNF, making it easy to define and extend. So at the top level, we have a program which consists of a sequence of statements. So the statement rule is recursive, so it keeps processing until it hits end of the input. So each statement types like if, while, define, assign, or say is handled by its own rule. So this makes the grammar more modular. We can also add new features like switch or functions if we plug in new rule. Yeah, and so the conditions are defined here with the fixed keyword structure using some Gen Z terms. Like for if construct, we have bet, then FR. So FR is for real, for real. So we similarly also have if else, which is bet, then now for real, for real. Yeah, so instead of a generic end, we use FR to close conditionals, so which keeps parsing unambiguously. So the loops also follow a similar structure. For while loops, we have on, got, do, done. And for the for loops, we have loop I from to do done. So again, the use of keywords like done helps to detect where the block ends. And the expressions are structured by precedence. So we have followed that so that it's important for having a correct evaluation. So here's how we have layered it. At the top, we have ternary expressions, which is the question mark and semicolon. Then we have the logical or, followed by and then not. Then it's followed by the comparisons, such as equals, greater than, less than. And then finally, we have the arithmetic, which is plus, minus, multiplication and division. So this will help us in ensuring something like, A plus B into C can be parsed in the right way, where the multiplication binds tighter than addition. So then at the lowest level, we have factors like the literals, which is number, boolean, string, or ID, and grouped expressions like EXPR for nested logic. So the key features of our language are, we have created Vani with Gen Z slang-based keywords so that it's more readable. It supports integers, boolean, as well as strings. It has built-in functionality for print, and we use the stay keyword for it. We have implemented for and while loops and conditional constructs using ternary and if-else statements. More on that. Yeah, so these are the keywords. As you see, the keyword bet, the rule is it starts an if statement. Na is for else. FR is to close the if or the if-else statement. Loop is the replacement for loop. And instead of the assignment operator, we have finna be. And for print, we have say. Yes. So these are our supported constructs. As earlier mentioned, conditionals, we have if else. Loops, we have while, which is on, God, do, done. Similarly, expressions, these are the expressions: arithmetic, logic, and comparison. And blocks, yeah.
Okay, so here we have our language overview. So this is essentially like the image in front of you is essentially the architecture that powers Vani. So it has a tokenizer which breaks the program into unit atoms called tokens. It passes those tokens to the parser, which essentially just takes it and builds an abstract syntax tree, and it validates the syntax of it, validates the correct structure. Then it passes to what we call evaluator, which I will leave Samuel to explain. Let's take a look at the tokenizer. These are the various different types of tokens, their examples and description. Tokens such as bet are used used for as commands. We have normal identifiers like variables or function names, such as x, y, total count, numbers, 0, even 3.14, operators, delimiters, and comments. Now, the tokenizer has a couple of responsibilities, such as converting the raw code into tokens, like I earlier mentioned, ignoring white spaces and comments, recognizing our specific keywords, numbers, and then at the end of it, sending all of the tokens to the parser. Next slide. Let's take a look at the parser now. Here we have the constructs, the example of said construct within our code, and the past form of said construct. So for assignment, we have y(x) gonna be 5, which is essentially saying assign the value of 5 to x. And for conditional, we have pet x plus 3 Loki for real, which essentially comes down to condition, then branch, and the else. Loops on guard x plus 10 Loki done, while we have 10 value, continue doing x, so on and so forth. Parse also has a set of responsibilities that it has to maintain. The main job of the parser is to build the abstract syntax tree. In order to build it, it needs to validate the structure and the order of the constructs. Please, same slide. Now, we have used Prolog DCG to implement this parser. In order to do this, we essentially use the Prolog DCG to implement this because it enforces ordering, nesting, and proper token sequence. After ensuring that we are passing the correct values, we need to check for its semantic correctness. Next slide. Semantic correctness is checked by the evaluator, but so here, y(x) finna e means to evaluate e and bind the result to x. Onboard c Loki be done is essentially while c is true, repeatedly execute p, and so on and so forth.
Yeah, so let's dive into the evaluator. So this evaluator module works in a custom Prolog interpreter. So this is considered to be the core part of our logic that actually runs the program written in our Gen style language. So let's break it down into simple parts. So the evaluator module is a runtime engine of our interpreter, and it starts with the eval program, which takes a list of statements and runs them one by one. While doing this, it maintains a dynamic environment, basically a list that stores all variables and their current values during the execution. If you move on to the next slide, Aditya. So let's go into the program and the statement evaluation. So when we call the eval/1 with a program statements term, the evaluator starts executing each statement one by one using eval statements/3. So it maintains something called an environment, just a list of variable value pairs, like a memory where variables are stored and updated. So the evaluator supports many types of statements, and it defines, adds a new variable to the environment, assign changes the values of an existing variable, say and print are like console log, they evaluate and print and display values. For control flow, if and else executes code based on instructions, while loop keeps running as long as the condition is true. And for the loop count, starts from start to end value and run a block each time. So each of these is handled in eval statement/3 to clearly match the statement types and take the action accordingly. And if you move to the next slide, Aditya, we do have expression and arithmetic handling. So the evaluator can process arithmetic like addition, subtraction, multiplication, division, and even nested expressions using parentheses. So it uses eval expression/3 to recursively compute results. So it also supports variables, strings, booleans, and even ternary expressions like condition, then, and else. Can you move on to the next slide, Aditya? And we also have conditions and logics. So for decision making, we have eval condition. So we use eval condition/2. So it supports comparisons like equals to, or greater than, less than, and then logical operators like and, nor, and not. So these are crucial for handling ifs and loops. We do also have environment operations. So to keep track of variable states, we have held per predicates like lookup/3. So it fetches a variable value, update/4. So it helps to change the variable value, and then update or define/4 used in loops to either define or update a loop variable. So in summary, the overall evaluator.pl acts like a virtual machine. So it takes a parse AS T, so the abstract syntax tree, and then brings to its life handling definitions, expressions, condition loops, and print statements while managing the environment dynamically. So let me walk you through how to install and run our custom interpreter for the ZenC language. Our interpreter is a modular and designed for simplicity. So the main entry point is the final execute.pl, so which is already posted in our GitHub. And we provided a convenient shell script, which is execute.sh to make it easy to run program from the terminal. So all the requirements are, so we'll just need to begin with SWA Prolog installed in our system. And then we need a unique base terminal or a WSL for Windows, and a program file written in a ZenC language syntax. How you can browse them under the data/programs, which are in our GitHub. So once the SWA Prolog is installed, so there's no compilation or building, so everything runs directly through the interpreter. So how it works behind the scene is, so in final execute.pl, we import 3 core modules, which are a tokenizer, parser, and evaluator. So the tokenizer breaks raw code into meaningful tokens, while the parser builds an abstract syntax tree from tokens, while the evaluator executes the AST and manages variable loops, conditions, and output. So the main predicate run/0, it reads a source file. In our case, it's under the data/program1 or program2. So that will be the source file from the command line using an argument, and then tokenizes and passes it, and then evaluates the AST and runs the program. So to run the program, so it has already been explained in our GitHub, so how to run it, but in a nutshell, so we just if it's in case of Mac, so we just simply run from that particular directory bash executor.sh. So this executor calls our final predicate.pl, and then we give our program in the ZenC language. So the shell script automatically launches SWA Prolog and loads final execute.pl, as I told before, while calling the run/predicate to return this input file. If program 1 contains valid syntax, it will be parsed and executed instantly, printing results, evaluating variables, and handling control flow using the logic defined in the evaluator.pl.
So let's go over the sample programs. We have added 7 sample programs for our code. We'll go one by one and execute them as well to see their output. So this is our first program. It's a very simple program where we have 2 assignments for x and y. We are trying to add them, and then we are printing the value of x. So x is 5 and y is 10. When we execute this, the output comes as 15. Coming to program 2, in this program, we are trying to define is cool as for real, and then we have a conditional construct where we are checking if it's equal to for real. We are saying you cool, otherwise we are saying you not cool. So let's try and execute this as well. Okay, so since the first statement is true, it says you cool. Moving on to program 3, we are defining num as a number 7. We are checking if it's greater than 5, then we have a print statement. So let's try and run this program. Okay, so as the number was greater than 5, we can see that it got printed as big num. Coming to program 4, we are showcasing loop here. So we have initialized count as 0, and till the count is less than 3, we are running a loop. And inside the loop, we are printing as well as incrementing the count. So as you can see, the program ran for firstly printed 0 as the value for 0 for it, then 1, and then 2. Since after 2 it exceeded to 3, it terminated there. Coming to program 4, it's a loop from 1 to 100, and on each iteration we are printing the value of I. So if you can see, so the program executed with printing the values for all the I from 1 to 100. Coming to program 6, here we are showcasing a ternary operator. We define mood as vibing. We are checking if the mood is vibing. We say it's keep going, otherwise we say take a break. Let's execute this. And yeah, it says keep going because the statement is true. Coming to our last program, here we have assignment for a and b variable, and here we are checking for both the statements. If a is equal to for real and if b is equal to cap, then we want to say logical pass. So let's execute this. Yeah, so it prints logical pass since both the statements are true. So these are the 7 sample programs we have implemented to showcase the capabilities of our language. Coming back to the slides, what's next? So we plan to implement and improve more on this by adding supports for more data types where user will be able to handle complicated cases and complicated data scenarios. Currently, we don't have a support for proper error messages while debugging. So we want to improve on that as well, where we showcase users that why the whatever input or the file has failed. So showcase proper error messages for them. And we also want to add support for providing inputs as to the program. So currently the programs are written. We want to add support to user can give custom input when they are executing and running the programs.